I'm Kevin McKee with the Computational Cognitive Neuroscience Lab at UC Davis. In this brief talk, I will be presenting results on how the brain may draw samples from posterior distributions. These are the four main points we'll consider. First, that synapses encode probability mass, that synaptic failure and lateral inhibition sample from encoded distributions, optimal failure probabilities can be learned, and finally, that sampling enables probabilistic action and reasoning. Although any input to a neural network may have many likely outcomes, without an explicit mechanism for probabilistically considering those outcomes, a neural network can only respond to the single deterministic expectation. Our theory relies on the observation that neurons have receptive fields, or tuning curves, that translate analog stimuli into neural firing rates. For example, in visual processing, neural firing rates correspond to different line orientations. Each neuron's firing rate increases as the line approaches its central, most preferred orientation. If we interpret neural firing rates as probability mass, then sending projections from one layer encode a probability distribution as population codes in the receiving layer. We propose that sampling from the distribution results from the combination of synaptic failure, known in machine learning as dropout, and lateral inhibition, analogous to the winner-take-all dynamics produced by a softmax distribution. Dropout results in a random subset of activations, then the most active neuron suppresses the others by lateral inhibition. If the dropout probabilities are tuned just right, the result is a representative sample from the distribution, which will occur with the encoded probability. Under this sampling framework, we prove that the optimal dropout probabilities are a nonlinear function of the weights shown here. From our result, we also obtain an approximate target for iterative local learning of dropout probabilities that only draws from the current state of the network during each iteration of sampling. When the dropout probabilities are all the same, around 0.5, the network can be seen to only sample from a small amount of variation around the maximum a posteriori. As dropout probabilities are learned, posterior samples become much more representative of the complete distribution. Various learning rules are possible. We prefer a simple fixed exponent to the target term previously shown, which produced minimal bias among the largest synapses. The results for that rule are shown in green. Learning rules that produce excessive bias in the largest weights will diminish the tails of the distribution, as you can see from the rightmost panel. We first check the accuracy of our results in a biologically constrained neural network by simulating a sequence of Gaussian distributions of increasing variance. The data are shown to the left, and the network samples over the entire input domain are shown to the right. Samples of the total posterior distribution are shown in blue, while samples of only the epistemic component of that distribution are shown in red. Specifically, the epistemic variance produces what might be classically known as the standard error of the mean, or more accurately for this model, the standard error of the maximum a posteriori. The dropout probabilities to produce epistemic uncertainty were derived from a mean field variational model based on the beta distribution. Epistemic uncertainty can be seen to narrow where data were most concentrated, then widen toward the edges of the most active receptive fields. Uniform priors were set for each neuron such that the network sampled uniformly from the output domain where no data were available at all, and so epistemic uncertainty was greatest. The matrices of learned weights and probabilities by three methods are shown below. Results from the local iterative learning rule match the analytic values closely. In the third matrix shown, dropout probabilities were learned per input neuron, whereas in the last matrix, learning was performed over the pooled projections from multiple input neurons. On the left, comparing both locally learned and analytically derived dropout probabilities shows that the standard deviation of the samples is close to the true data generating standard deviation. On the right, we found that the epistemic uncertainty, taken here as the standard error of the maximum a posteriori, was approximately the same when weights were randomly dropped out as when they were generated from beta distribution, with the latter serving as a quasi-analytic point of reference. Additional simulations were run to demonstrate sampling from the network more broadly, when multiple modes and heteroskedasticity are present in the data. The samples in blue can be seen to accurately replicate the data distribution, or aleatoric uncertainty, while the samples in red show exactly where the upper cluster becomes more likely, that is, more dense than the lower cluster. We implemented our sampling scheme of synaptic failure and lateral inhibition in a spiking neural network with the bimodal data simulation shown previously. It can be seen here that the learned synaptic weights shown above have encoded the conditional probability distributions for each value of the input. When the input neurons are active, the output activations represent the whole population coded distribution. Here, we are looking at the synaptic weights projecting from a single input over a long time course. The weights are randomly masked, producing random subsets of the encoded distribution. With dropout, the output activations become a sequence of samples from the complete distribution. Dropping out the largest weights enables activation of the distributional tails and other outliers. For more information, you can see our preprint available on arXiv, the link below, or you can feel free to contact me at my UC Davis email address.